We are in week 6 already, and we are starting unit 3. Both units 3 and 4 of this class deal with measurement. Unit 3 deals with the units of measurement and how we work with them. And then we throw in there's some algebra that gets combined in with it here for unit 3. And then in unit 4, we look at the measuring devices and how those are used. And that's actually kind of interesting to see who has experience and who doesn't with those. So we're going to start off today with Unit 3 with something that seems like it might be slightly unrelated, but it's actually a very important topic when it comes to measurement. And it's things that look like this. We've talked about these exponents before, and how an exponent has two parts to it. The 10 in this case is called the base. That is the number that is being acted upon. The 3 here is what is called the power. That is telling us how many times that base is repeated in our calculation. Our 10 to the third over here means, the 10 means that we're repeating a 10. The 3 means there's 3 of them multiplied together. So 10 times 10 times 10, or 1,000. Now, many of us have learned some shortcuts for our powers of 10. 10 to the power of 5, which is going to be 10 times 10 times 10 times 10 times 10, ends up being 100,000. But rather than having to actually multiply them out, like I said, many of us have learned some shortcuts for our powers of 10, where what we were taught was the power of 10 just tells us how many zeros come after the 1. So 10 to the third is a 1 with 3 zeros after it. 10 to the fifth is a 1 with 5 zeros after it. So 10 to the seventh would be a 1 with 7 zeros after it, or 10 million. Well, I want to talk a little bit about what would it mean to have 10 to the power of 0. This doesn't make much sense. How do we have 0 tens multiplied together? I mean, 10 to the 1 is a little tricky, but we can kind of reason it out. It's just a single 10 sitting there with nothing happening to it. So 10 to the power of 1 is just 10. In fact, whenever we see a number without a power written there, it really is implied that there's a power of 1 on it. We just don't write it in. We don't waste the ink on it. But that 10 to the power of 0 just really doesn't fit in with the definition of power. So we do the same thing we did with our multiplication of two negatives. We look for a pattern. Now we had 10 to the power of 4 was 10,000. And 10 to the power of 3 is 1,000. 10 to the power of 2 is 100. Well, let's look for that pattern here. We see that when the power here is reduced by 1, from 4 to 3 is subtracting 1. Our result is divided by 10. 10,000 divided by 10 is 1,000. 1,000 divided by 10 is 100. That occurred when we reduced the power by 1 again. So if we keep going, let's see if that pattern holds up, if it continues. Well, we've already said that 10 to the power of 1 is just 10. So it appears to work. We reduced the power by 1 again. The result was divided by 10. So from 100 to 10 is dividing by 10. So when we go to the next step, 10 to the power of 0, we reduce the power by 1. We have to divide the answer by 10 again. 10 divided by 10 is 1. 10 to the power of 0 is just 1. In fact, this pattern holds very similarly for any number that we put in there as the base. Anything to the power of 0 is 1. 7 to the power of 0 would be 1. 243 to the power of 0 would be 1. X to the power of 0 is 1. Anything to the power of 0 is 1. That's worth making a note of because I have a little bit of a twisted sense of humor. And I wouldn't put it past me on a quiz or a test to have an extra credit question that looks something like this. And ask you what that equals. Well, because all of this is to the power of 0, none of this in here matters. Anything to the power of 0 is 1. That would work out to be 1. So, like I said, it's worth making a note of because I know myself I'm going to be tempted to do that to you at some point. Well, now that we've hit the power of 0, we can start talking about what does it mean to have a negative power? 10 to the negative 1. Well, once again, we reduce the power by 1. Our result should be divided by 10. Well, 1 divided by 10 is 1/10. 10 to the negative 2, if we divide by 10 again, that's 1/100th. Oops, 100th, not 1,000th. 10 to the negative 3, we divide by 10 again, that's 1/1000th. And we can see there's actually a pattern developing here with the negatives. 10 to the negative 3 actually relates to 10 to the positive 3. It's just reciprocals. 10 to the negative 3 is just the reciprocal of 10 to the positive 3, or 1 over 10 to the positive 3. That brings us to some rules for exponents. If we have exponents with the same base, that's very important, exponents with the same base. That same base is vital to combine them. What do I mean by that? X to the third and x to the seventh have the same base. Both of them have a base of x. So we can combine them. If they don't have the same base, we cannot combine the exponents. If I have 10 to the third times 10 to the fifth, well, 10 to the third is 3 tens multiplied together. 10 to the fifth is 5 tens multiplied together. If I multiply those all together, we have 1, 2, 3, 4, 5, 6, 7, 8 tens all being multiplied together. That's 10 to the power of 8. Well, some of you may have seen a shortcut for this. 10 to the third times 10 to the fifth. When I am multiplying exponents with the same base, I can just add the powers. 3 plus 5 is 8, so that's 10 to the 8th. If I had, hold on. Oops. Go up to a blank page, I guess. If I have 10 to the 9th times 10 to the 13th, again, I am multiplying exponents with the same base. They both have a base of 10. So my result is going to have a base of 10. I keep the same base, and I'm going to add the powers. 9 plus 13 is 22. It doesn't have to have a base of 10. It can be x to the 5th times x to the 8th. Those do have the same base. They both have a base of x. So my result has a base of x. And I add the powers. 5 plus 8 is 13. So it's x to the 13th. Y to the 9th times y to the negative 2. Throw a little curveball in there. They both have a base of y, so my result's going to have a base of y. I'm going to add the powers. 9 plus a negative 2. Well, 9 plus negative 2 is 7. So that gives me a result of y to the 7th. So we might have 10 to the negative 6th times 10 to the 4th. We combine those. Again, they both have a base of 10, so our result has a base of 10, and it's negative 6 plus 4, which is negative 2. That's 10 to the negative 2. 10 to the negative 9th times 10 to the negative 5th. Well, again, both of those have a base of 10, so our result has a base of 10. We add the powers. Well, that's negative 9 plus a negative 5, which is a negative 14. So that's 10 to the negative 14. So beware of the negative powers in our exponents. They are a little tricky to work with, but I'm confident we can handle them at this point. Well, the next task that we can combine looks like this. We might have 10 to the 5th divided by 10 to the 3rd. Well, again, 10 to the 5th is 5 tens multiplied together. 10 to the 3rd is 3 tens multiplied together. Now, we saw with our fractions, first of all, a division and fractions, remember, are interchangeable. We can go back and forth from one to the other. So even though this is 10 to the 5th divided by 10 to the 3rd, we can treat it like a fraction. And when we did fractions, remember, we could divide numerator and denominator by the same number, or we could cancel out factors. That's exactly what we're going to do here. We can cancel out a 10. We can divide out a 10. We can divide out another 10. And we can divide out a third 10. And what we're left with, on bottom, everything divided out. So that's just a 1. And top, 10 times 10, well, that's just 10 to the 2nd power. Anything over 1 is just itself. So 10 to the 2nd over 1 is just 10 to the 2nd power. So we might have 10 to the 18th over 10 to the 11th. So we know that we can just subtract the powers here. This is going to be 10 to the 18th minus 11. 18 minus 11 is 7. That's just 10 to the 7th power. We might have 10 to the 5th divided by 10 to the 14th. Again, we just subtract powers. We have to be a little bit careful here, though. Make sure it's always the top one minus the bottom one. It's the dividend minus the divisor, if you want to use that terminology. The one we're dividing by has to be the power that is subtracted. This is 10 to the 5 minus 14. Well, 5 minus 14 is a negative 9. That's 10 to the power of negative 9. So what if we have 10 to the 7th divided by 10 to the negative 5th? Well, once again, we are subtracting powers. That's 10 to the power of 7 minus a negative 5. Recall that we changed minus a negative to adding the opposite. That's plus a positive 5. So 7 plus 5 is 12. That's just 10 to the 12th. Or we might have 10 to the negative 6 divided by 10 to the 9th. Well, again, that's 10 to the negative 6 minus 9. Remember, the one we're dividing by is the one that's subtracted. Well, negative 6 minus 9 becomes negative 6 plus a negative 9, adding the opposite. Subtracting a positive 9 is the same as adding a negative 9. Well, negative 6 plus negative 9 is a negative 15. That's 10 to the negative 15. Or examples like 10 to the negative 7 divided by 10 to the negative 4. That's 10 to the negative 7 minus a negative 4. Well, negative 7 minus a negative 4. The negative 7 doesn't change, but subtracting a negative 4 becomes adding the opposite of negative 4. Well, the opposite of negative 4 is a positive 4. So that is 10 to the negative 7 plus 4. Negative 7 plus 4, of course, is just negative 3. Or we might have 10 to the negative 9 divided by 10 to the negative 15. That's 10 to the power of negative 9 minus a negative 15. Well, negative 9 doesn't change. Minus a negative 15 becomes plus a positive 15. So 10 to negative 9 plus 15 is a positive 6. So 10 to the negative 9 divided by 10 to the negative 15 is 10 to the positive 6. Like I said, beware those rules of powers. They come back to haunt us over and over again throughout the course. Well, we also have a power of a power. Ten to the third to the power of 4 means that we have 4 of these 10 to the thirds multiplied together. But remember, each of those 10 to the thirds is 3 tens multiplied together. So if I multiply all of them together, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 tens being multiplied together. That's 10 to the power of 12. Well, you might notice that 12 can be derived from those powers that are used. You may have seen that when we have a power of a power, the result is you multiply the two powers. 10 to the third to the power of 4 is 10 to the power of 3 times 4, or 10 to the 12th, just like we got up here. So we could have x to the 5th, the power of 7. That's x to the 5 times 7 is 35. Or y to the 4th, the power of 10. Y to the power of 4 times 10 is 40. 10 to the 6th, the power of 9. Well, that's 10 to the power of 6 times 9, or 10 to the 54. Well, once again, our negatives can be a factor. We might have 10 to the 5th to the power of negative 8. That's 10 to the power of 5 times negative 8. Well, 5 times negative 8 is a negative 40. So that's 10 to the negative 40th. We might have 10 to the negative 6th to the power of 7. That's 10 to the power of negative 6 times 7. Well, negative 6 times 7 is a negative 42. That's 10 to the negative 42nd. Or I might have 10 to the negative 4, the power of negative 11. 10 to the negative 4 times negative 11. Negative 4 times negative 11. Remember, a positive times or negative times a negative is a positive. That's 10 to the 44th power. Well, let's combine some of these together. Something like this. 10 to the third times 10 to the 8th over 10 to the 5th. But remember that fraction bar says we have to do everything on top first, then everything on bottom separately, and then combine the two. So on top here, 10 to the third times 10 to the eighth, we're multiplying exponents, so we add the powers. 3 plus 8 is 11. There's nothing to do on bottom, so that's just going to stay 10 to the fifth. Now we're dividing here like bases. They're both bases of 10. So we subtract the powers. 11 minus 5 is 6, so that is 10 to the sixth. We might have 10 to the seventh times 10 to the negative 11th over 10 to the negative 9th times 10 to the third. So again, we combine what's on top first. 10 to the 7th times 10 to the negative 11th. We add those powers. 7 plus negative 11 is negative 4. That's 10 to the negative 4. Then we do what's on bottom. 10 to the negative 9th times 10 to the third. Again, we're multiplying like bases, so we add the powers. Negative 9 plus 3 is a negative 6. And now at this point, we're dividing. So that's negative 4 minus a negative 6, which is a positive 2. Remember, negative 4 minus a negative 6, negative 4 plus a positive 6, which is a positive 2. We have 10 to the 8th divided by 10 to the negative 3 times 10 to the negative 6th divided by 10 to the 5th. Here we have to do the divisions first. 10 to the 8th divided by 10 to the negative 3. Well, 8 minus a negative 3 is 11. That's 10 to the 11th. Over here, 10 to the negative 6 divided by 10 to the 5th. We subtract negative 6 minus 5 is negative 11. Now when we multiply these, we're adding powers. 10 to the 11th times 10 to the negative 11th. Well, 11 plus negative 11 is 0. That's 10 to the power of 0, which can be written as just 1. We can combine powers in with this. We might have 10 to the 8th times 10 to the negative 3rd, the power of 4. Again, parentheses tell us we have to do what's inside here first. 10 to the 8th times 10 to the 3rd, 8 plus, or 10 to the negative 3rd, I should say. 8 plus negative 3 is 5. That's 10 to the 5th. Now we do that power of 4 outside the parentheses. 10 to the 5th to the power of 4. We multiply. 5 times 4 is 20. So that's 10 to the 20th. We might have 10 to the 7th times 10 to the 5th over 10 to the 8th, power of negative 3. So again, we have to do what's inside the parentheses first. Fraction bar says we have to do what's on top first. 10 to the 7th times 10 to the 5th. We're adding powers when we multiply, so that's 10 to the 12th. Nothing to do on bottom of the fraction bar, so that's just going to stay there. Now we have to do the division. 10 to the 12th divided by 10 to the 8th. We subtract powers. 12 minus 8 is just 4. And now we have the 10 to the 4th to the power of negative 3. 10 to the power of 4 times negative 3 is a negative 12. Or we might have 10 to the 11th times 10 to the 4th over 10 to the 9th over 10 to the 8th over 10 to the negative 5th times 10 to the negative 3. The power of, let's go negative 5 just for fun. So we have to do inside the parentheses first. Fraction bar is telling us to do what's on top first. Well, on top, first thing we have to do is this division here because it's in a fraction bar. So the 10 to the 11th doesn't change. 10 to the 4th divided by 10 to the 9th. I'll make this a little closer here. 4 minus 9 is negative 5. That's 10 to the negative 5th. Next, I'm going to combine those. 10 to the 11th times 10 to the negative 5th. They're multiplying, so I'm going to add the powers. 11 plus negative 5 is a positive 6. Now you notice I left the bottom blank because now I have to go back and do the bottom of that fraction bar. So 10 to the 8th divided by 10 to the negative 5th. Well, 8 minus a negative 5 is 8 plus 5, or 13. And then we have to do the multiplication. 10 to the 13th times 10 to the 3, or negative 3, I should say. Go away. So 10 to the 8th times 10 to the 13th times 10 to the negative 3. 13 plus negative 3 is 10. That's 10 to the 10th. Now at this point, I can divide. I've done everything on top of the fraction bar and everything on bottom. 10 to the 6th divided by 10 to the 10th. Well, 6 minus 10 is 10 to the negative 4. And now I just have to take that to the power of the negative 5. 10 to the negative 4 to the power of negative 5. I multiply powers. Negative 4 times negative 5 is a positive 20. There are a lot of those in the homework. Make sure you do plenty of examples of those. I want to go back and talk a little bit about our place values. Now that we've got these powers of 10s in here. If you recall, we had said, ones, tens, hundreds, thousands, 1,000s, 10,000s, 100,000s, on up the line. Of course, this was 1/10th, 100th, 1,000th, and counting down that way. But with what we've seen today, we know that all of these are powers of 10. 1 is just 10 to the power of 0. 10 is 10 to the power of 1. 100 is 10 to the 2. 10 to the 3rd is 1,000. 10 to the 4th is 10,000. 10 to the 5th is 100,000. 10 to the 6th is 1,000,000. And we can keep going up. 10 to the negative 1 is 1/10th. 10 to the negative 2 is 1/100th. 10 to the negative 3 is 1,000th. 10 to the negative 4 would be the 10,000th, and 10 to the negative 5, and we can keep going in that direction. Our place values are powers of 10. That's why we refer to our number system as a base 10 number system. Our place values are exponents with a base of 10. Now, often we'll take a number like 3,900,000, and we will abbreviate it by calling it 3.9 million. Well, instead of writing out the millions place value, we could actually just say it's 3.9 times 10 to the 6th is the numerical place value for that millions place. Some of you may notice this as scientific notation. What scientific notation does is it identifies the first non-zero digit of the number. Then we put the decimal after it. And we name its place value. So if I have 82,000, my first non-zero digit is the 8. The decimal is going to go after it, and I name its place value. So in scientific notation, that would be 8.2, and the 8 is in the 10 to the 4th. That's 8.2 times 10 to the 4th. Or after the decimal, we might have something like 0.00073. The 7 is my first non-zero digit, so I'll put the decimal point after it and name the place value of the 7. So that's 7.3 times 10 to the negative 4. Well, obviously, we don't want to have to draw out the place values like this when we convert our numbers. So let's look at what happened here with the 3.9 million. The decimal point on that started out right here, and we moved it over to here. It had to go 1, 2, 3, 4, 5, 6 decimal places. Notice the power of 10 is 10 to the 6th. For 82,000 here, the decimal point started here, and it went to there. It had to go 1, 2, 3, 4 places. Notice 8.2 times 10 to the 4th. That 4, power of 4, corresponds to having moved 4 decimal places. Over here, the decimal point started out here, and it moved to here. It went 1, 2, 3, 4 places. Again, notice there's a 4 on our power of 10. The difference is this is a negative 4, and this over here was a positive 4. How do we know whether it's positive or negative? Well, these are large numbers. They're bigger than 1. Numbers that are larger than 1 have place values that have positive powers of 10. This was a small number here. It was smaller than 1. Numbers that are smaller than 1 have place values that are negative powers of 10. So if I have something like 460 million and I want to put that into scientific notation, well, the 4 is my first non-zero digit, so the decimal is going to go after it. That's going to be a 4.6. Decimal point started out here. It had to move 1, 2, 3, 4, 5, 6, 7, 8 places. That was a large number, so it's a positive 8. 10 to the positive 8. I might have 0.0000073. Again, this is my first non-zero digit, so I'm going to put the decimal point after it. So it's going to be 7.3. This is a small number. It's smaller than 1, so I know it's going to be a negative power of 10 in my place value. And the decimal moved 1, 2, 3, 4, 5, 6 places. That's times 10 to the negative 6. Going the other way is just as simple. If I have my scientific notation and I want to convert it to a power of 10 or to a decimal number, I might have 5.3 times 10 to the negative 5. Well, again, I'm going to take my 5.3 and I have to move my decimal point one direction or another. The negative 5, it's a negative, which tells me that this is a small number, so I have to move my decimal point to make it smaller 5 places. So I go 1 spot, then I have to add zeros to go 2, another 0 to go 3, another 0 to go 4, and another 0 to go 5. That is 0.000053. Or we might have 7.8 times 10 to the 7th. Well, again, we'll start with that 7.8. And we know we have to move that decimal point to put it back in decimal or standard notation. This is a positive power of 10, so we know this was a large number. So we have to move that decimal point 7 places to make this larger. So we can go 1, to go 2, we've got to add a 0, another 0 to go 3, 4, 5, 6, 7. So that is 78 million as a decimal number. So we can convert rather readily from scientific notation to our standard decimal notation by moving the decimal point. One last thing I want to go over here. We talked about fractions in the last unit. But what does it mean to have a negative fraction, like a negative 2/3? Well, there are actually 3 different ways that we can work with that number. We can work with it as a negative 2/3. So the whole thing is negative. Now, when I say the whole thing is negative, I'm saying we're treating the 2/3 as a unit, and it's negative. Or we can treat it as a negative 2/3. A negative divided by a positive is still a negative, so it means the same thing as this. Or we can treat it as a 2 divided by a negative 3. Again, a positive divided by a negative is a negative, so it still means the same thing. The reason we do that is there are times where it's easier to have the negative out in front and just treat it as a negative fraction, like this. Negative 2/3 times negative 3/5. Well, I can just cross cancel the 3's. 3 divided by 3 is 1 in both cases. 2 times 1 is 2. 1 times 5 is 5. A negative times a negative is a positive, so that's just a positive 2/5. That works out just fine. But there are times where it might be beneficial to have it as either one or the other. We haven't talked much about algebra yet, but we might have negative 2/3 times 3x minus 5. When we do that, it's often easier to put that negative with either the 2 or the 3. I would put it with the 3 or the 2. And when we multiply, of course, we have to make that 3x minus 5 over 1. And now we can multiply that negative 2. We'll talk about doing that operation with our algebraic numbers later on in this unit. But for right now, know that it's easier to put the negative with the numerator and multiply it through rather than have it just right out in front of the fraction. The key is negative 2/3 cannot be negative 2 over negative 3. Because a negative divided by a negative is a positive. That does not equal negative 2/3. So be careful not to do that. A negative fraction, either the numerator is negative or the denominator is negative, but not both. Okay, so for homework, we have 3 pages today. Page 121. This is exercise 2.4, 1 through 45, the odds. That's working with some of those fractions with negatives. Page 125, this is exercise 2.5, 1 through 29, the odd, is working with those powers of 10. Make sure you do some of the more complex examples there. And page 130, exercise 2.6, 1 through 57, the odd. This is on converting scientific notation. Now, again, I realize there's a lot of problems there. Make sure you do some of the more difficult ones in each section, especially this section here. Make sure you do some of the more difficult combining the powers examples. There will be some coming up on a quiz, probably Thursday, and there will be some coming up on the next unit test. Okay, I'm going to shut off the recording here. I will give you guys the last 9 minutes here to work. I will stay on network.